And this property is called property is called translation invariant. That's lambda. Oh, sorry. Translation invariant. Next is the and lambda star of A is equal to lambda star of x plus A for every x in R. This property and this property is called translation invariant. So that is the lambda star is Lebesgue outer measure is translation invariant. Proof. This one is very simple because you can easily verify that. You can see this since A is subset of union n runs from 1 to infinity A and Bn, because here the submeaning is the class of semi-closed intervals, so that union n runs from 1 to infinity A and Bn is union n runs from 1 to infinity A and Bn, semi-closed interval. It's subset of this if and only if x plus A is subset of union n runs from 1 to infinity x plus A n comma x plus Bn. So therefore we have the infimum. Therefore, we have this infimum of summation is n runs from 1 to infinity. This Lebesgue measure of A and Bn, which is equal to actually Bn minus An, where A is subset of union A and Bn is same as the infimum of summation n runs from 1 to infinity Lebesgue measure of An plus x or x plus An Bn plus x, such that x plus A is subset of union n runs from 1 to infinity An plus x comma Bn plus x. So both are same. Both the infimums are same. So, but by definition, this is lambda star of A, and by definition, this one is lambda star of x plus A. So that proves Lebesgue measure is a translation invariant. So now we prove this A is Lebesgue measurable if and only if x plus A is Lebesgue measurable. So to prove A is Lebesgue measurable if and only if x plus A is Lebesgue measurable, we use the following identity. What are those identities? Following identities. So we have two identities here. One is E intersection x plus A is same as x plus E minus B, x plus E minus B intersection A, and E plus x plus A intersection, E intersection x plus A complement, E intersection x plus A complement is equal to B plus E minus B plus E minus B. Sorry, it's here X. It's X here, and this is here X, and that's X here. It's X plus E minus X intersection A complement. E minus X intersection A complement. So we use these two identities to prove the result. So you can easily verify these two identities because they are all sets. You have to prove the set inclusion actually. That's very simple. Now you can see that now lambda star of E intersection X plus A plus lambda star of E intersection X plus A complement is equal to lambda star of it's X plus it's E intersection, that's equal to X it's E minus X, so it's not here X plus, it's E minus X intersection A. So it's E minus X, or it's actually X plus here, but Lebesgue measure of X plus E minus X intersection A is same as E minus X intersection A. So it is just E minus X intersection A by the result that Lebesgue measure is translation invariant. Lebesgue measure of this set is equal to Lebesgue measure of E minus X intersection A plus Lebesgue measure of this one. Again apply the translation invariant property. It will be E minus X intersection A complement. And here you can easily verify that A is measurable if and only if X plus A is measurable, because both are equal. So if suppose X plus A is measurable, then this will be equal to Lebesgue measure of E. But at the same time it will also be equal to Lebesgue measure of E minus X, so which proves A is measurable. Because any subset of R can be written as E minus X, so you can do that. And conversely, if A is Lebesgue measurable, then this will be equal to Lebesgue measure of E minus X, which is equal to Lebesgue measure of E. And it is same as this one. So that means X plus A is measurable. So you can easily verify it. Now I leave this verification for you. Verify that from this equation, we can easily conclude that X plus A is measurable if and only if A is measurable. And also you have to use the fact that the Lebesgue measure of E minus X is same as Lebesgue measure of E, because the Lebesgue measure translation invariant. Lebesgue measure is translation invariant. So now we have an example. In this example, we will show that there exists a non-Lebesgue measurable subset of R. So let's consider the measure space. Consider the measure space. This R with class of semi-closed intervals and Lebesgue measure, where S is a class of semi-closed intervals. Then we know that this interval 0, 1 is measurable. This is already proved it's measurable. So we define, let's denote this by E equal to this. We define a relation on E. We will show that there is a subset of this interval 0, 1 which is not Lebesgue measurable. So define a relation on E by X is related to Y if and only if X minus Y is a rational number. Then you can easily verify that this relation is equivalence because every element is related to itself as the difference of x minus x is 0, which is a rational number, so it's an equivalence relation. Second, it is solution, because if x minus y is rational, then y minus x is also rational. And third, it's also transitive, because whenever x minus y is rational and y minus z is rational, then their sum, which is equal to x minus z, which is also rational. So this relation is an equivalence relation. So then this is an equivalence relation. Equivalence relation. So therefore we can partition interval 0, 1 into its equivalence classes, disjoint union of equivalence classes. Therefore interval 0, 1, which is equal to E, can be written as a disjoint unions of equivalence classes. Equivalence classes. Now I define a set which exists by axiom of choice. I define a set F. Let F is the set of all points which precisely intersect at one point with each equivalence classes. Let F be the set of points in 0, 1 which intersects with each equivalence class, because equivalence class is a subset of 0, 1, with each equivalence class at exactly one point. I will explain it. Suppose if we have two equivalence class for some set, say for 0, 1, suppose we have two equivalence class. One is 0 to 1 by 2, and second is suppose 1 by 2 to 1. Suppose, for instance, here it's not the case, it cannot have these two, you cannot have only these two equivalence classes here, but to clear this concept, to clear this idea of selecting one point from each equivalence class, so let's take, suppose these two are equivalence class of this set 0, 1, then I choose one point from this. Suppose I will choose, say, 1 by 4, and one point from this set, say it's equal to 1, because 1 is the set. This is your set F. So F is the set which intersects with exactly one point from each equivalence class, because there are only two. This 1 by 4, 1, it intersects with this equivalence class at 1 by 4 only, and it also intersects with this equivalence class at only one point, that's 1 here. So in this this F is the set like this. So it intersects with each equivalence class precisely at one point. Such a set always exists by axiom of choice. Such a set always exists by axiom of choice. Axiom of choice actually states that if we have a given class of sets, then we can construct a set which contains exactly one point from each class, from each member. Suppose we have 10 sets. Say we have suppose 5 sets, suppose A1, A2, A3, A4, A5. We choose one point from each set and construct a new set A, which contains exactly one point from each set. So this is looks trivial. This is simple in case the sets are finite. We have a finite collection, but in case of uncountable collection, we say this is true by axiom of choice. It's by axiom of choice. Such a set always exists by axiom of choice. Okay. So we will show that this set F is not measurable. So then this f is a subset of 0, 1. We show that f is not Lebesgue measurable. We show that f is not Lebesgue measurable. So let's take the enumeration of rational numbers because rationals are countable. Let Rn n greater or equal to 1, R1, R2, so on be the enumeration of rationals, be the enumeration of rationals, not all rationals, but rationals which lies in this interval -1 to 1. Let's take this enumeration and define a set and define Fn, which is equal to Rn plus f, which is equal to the points Rn plus A such that A belongs to f. Let's define this set. So we need to show that our the set f is measurable. F is measurable. So we assume on contrary that f is not measurable. Assume on contrary that f is not Lebesgue measurable. Then by previous lemma Rn plus f is also not Lebesgue measurable. Then Fn, which is equal to Rn plus f, is not Lebesgue measurable. Not Lebesgue measurable. So for all n greater or equal to 1. Also, this one can easily verify that these Fn's are disjoint by using the relation, equivalence relation. You can easily verify that. We can easily verify that. So we assume that suppose there is an element in the intersection, and finally you arrive at a contradiction. So we can assume that Fn intersection Fm is 5 for n not equal to, and they are disjoint. They are disjoint. So we can not assume. It's we can easily verify that. It's not our assumption. This can be verified. We can easily verify that Fn's are disjoint. Fn's are disjoint. So these Fn's they are disjoint sets. This you can easily verify they are disjoint sets. They are disjoint. So they are disjoint. So also this and we have one more thing that Lebesgue outer measure of Fn is same as Lebesgue outer measure of Fn. It is already done in the lemma because Lebesgue measure is translation invariant. This is true for all n greater or equal to 1. Okay. Now you can easily verify this 0 1. It is subset of union n runs from 1 to infinity Fn, and which is subset of the interval -1 to 2. I will leave this as an exercise for you. So you verify this. You verify this. This one is simple because 0 1 is subset of Fn. 0 1 is always subset of Fn. it's simple, huh? And this this follows, or you can say this follows from this, because those orange, they are the rational numbers between -1 and +1, and you can choose a suitable point from the equivalence class, so that this will be, so you can verify this by using that relation. And this one is trigger. This one is true because it's Rn plus f. Rn lies between -1 and +1, and Rn lies between 0 and 1. So it's -1 to +1 and 0 to 1. Let's add these. It's -1 to +2. So this part is triggered. So you need to verify this part because here the points are, it's Rn plus a real number which lies between, A is a real number, A is a point in the f is substub 0 1, interval 0 1, and Rn lies between -1 and +1. So when we see Rn plus A, it will be less or equal to 2 and greater or equal to -1. So that 0 plus 1. So it lies in this interval 0 1, -1 2. That's simple. So now let's apply the Lebesgue outer measure on both sides. The Lebesgue outer measure 0 1 is less or equal to Lebesgue outer measure union A runs from 1 to infinity Fn, and Fn is our measurable. It's less or equal to Lebesgue outer measure -1 to 2. So let's look at this. It's 1 less or equal to, and here apply additive property because they are measurable and they are also disjoint. It is summation and runs from 1 to infinity Lebesgue outer measure of Fn, that's less or equal to 3. So this means 1 less or equal to summation and runs from 1 to infinity, but Lebesgue measure of Fn is same as Lebesgue measure of F, it's less or equal to 3. So this will be n times because you are adding n times this, n approaching to infinity. Yeah? So you are adding this infinite number of times, but it lies between 1 and 3. So if it is finite, if you add any non-negative number, a fixed non-negative number, infinite because it's a fixed number, Lebesgue measure of P. Suppose it is non-negative, it is positive number, and if you add it infinite number of times, it will be infinite. It will be, so it cannot be less or equal to 3. So that's a contradiction. Therefore, it must be equal to 0. But on the other hand, if it is equal to 0, then its sum is also equal to 0. So this sum is equal to 0, which is greater or equal to 1, which is again a contradiction. It's a contradiction. A contradiction. Because if you take this inequality, then in this inequality, this Lebesgue measure of P must be equal to 0. But on the other hand, this cannot be equal to 0 because it is greater or equal to 1. So that means we arrive at contradiction. Therefore, our assumption that f is measurable is wrong, hence f is not measurable. So this is an example of non-measurable set. So now we prove certain interesting properties of measurables, Lebesgue measurable sets. First, we show that Lebesgue measure of any singleton set is 0 for every x in R. Every singleton set. So let's prove this. Since for all epsilon positive solution, for all epsilon positive, x belongs to the following set: x to x plus epsilon. So that is the singleton set x is subset of x plus epsilon. So it's a cover actually because it's a number of semi-ring. So that means Lebesgue outer measure of this singleton x should be less or equal to the Lebesgue measure of this, which is equal to epsilon. So letting epsilon approaching to 0, this is true for all epsilon positive, which means Lebesgue measure of singleton set is 0. So from this, by using this fact that Lebesgue measure of a singleton set is 0, we will show that Lebesgue measure of every countable set is 0. Lebesgue measure of every countable set is 0. Lebesgue measure of f is 0 if f is countable subset of R. So since f is countable, therefore we can write f as a countable union of singleton sets. So let's suppose that this is a enumeration of f. R1, R2, they are the members of f because it's countable. So, and they are also disjointed pairs, R1, R2, so on. So we can see that Lebesgue measure of Fn is equal to summation n runs from 1 to infinity Lebesgue measure of a singleton Rn, but Lebesgue measure of singleton set is equal to 0. So this is equal to 0. So Lebesgue measure of every countable set is 0. And any set having Lebesgue measure 0, so that means it's actually a null set. Countable sets are null sets in the real life. So hence f is measurable. This also means f is measurable. F is Lebesgue measurable. So therefore every countable subset of R is measurable. So therefore every countable subset of R is measurable. In particular, Q is measurable because Q, the set of rationals, is a countable subset of R. It is measurable. Therefore, its complement, the set of irrationals, is also measurable. So they are measurable sets. But the interesting question is that does there exist any set which is uncountable but still its measure is 0? Does there exist a set C such that C is subset of R such that C is uncountable but still its Lebesgue measure is 0? And the answer is yes. And such a set is called a Cantor set that we will prove in coming lectures. There is a set which is uncountable but still that set has Lebesgue measure 0. So next, now suppose we have an interval I which is equal to 0, 1. Then I can write it as union of two sets, where A is set of rationals in 0, 1, A is set of rationals in 0, 1, and B is set of irrationals in 0, 1. These are two sets. A is set of rationals in 0, 1, B is set of irrationals in 0, 1. 0 1 interval is equal to rational union irrational. Then you can see that Lebesgue measure of I, which is equal to Lebesgue measure of the interval 0, 1, which is equal to Lebesgue measure of that union series. Both are measurable sets, as you know that set of rationals is measurable, set of irrationals is measurable. This is okay. This is our full space, and they are both measurable sets here. Because this A is measurable, its measure is 0, therefore it's measurable, and B is the complement of this B in this space 0, 1. So therefore B is also measurable. They are measurable sets, and it's equal to then Lebesgue measure of A plus Lebesgue measure of B. But what's Lebesgue measure of A? It's equal, here on this side it's equal to 1, and on this side it's equal to 0 plus Lebesgue measure of B. So that means the Lebesgue measure of the irrationals in the interval 0, 1 is 1. Because Lebesgue measure of rationals in the interval is 0. So it means that there exists a set, say A, whose Lebesgue measure is equal to 1, but still this A does not contain any interval. It does not contain any interval, but still its measure is equal to 1. So it's a set, it's not like discrete set, it's a set of irrationals actually. They are very dense in this interval 0, 1, they are dense in interval 0, 1, and that set of irrational does not contain any interval, because every interval contains rationals as well as irrationals, and the Lebesgue measure of that set is 1. So in other words, so if the Lebesgue measure of a set is not equal to 0, so we cannot say that this A contains an interval. A contains an interval. But next lecture, in coming lectures, we will show that If the Lebesgue measure of A is not equal to 0, then the then this difference, algebraic difference of these two sets, it must contain an interval. What's A minus A? A minus A means x minus y, where x comma y both belongs to A. It's the algebraic difference. So we will show that if the Lebesgue measure is positive, it's not equal to 0, then this algebraic difference of the set A must contain some interval. So that theorem is called as Steenhuy's theorem, that we will prove in coming lectures. So thank you. That's the end of this lecture.